Good afternoon, and thanks for coming back. So, this is in a way one of the punchlines of the part of the course having to do with life as defiance. So, the reason I say that is what we're going to do now is we're going to examine a real world case study in which a simple interpretation of the biological battery leads to a process that, if we weren't careful and we watched it, we would be convinced that the process was occurring in a way that, in a sense, appeared to defy the second law of thermodynamics. And what I'm referring to is, for example, the way that sugar molecules will be transported up their gradient from the outside of the cell into the cell, where the concentration inside of the cell would be higher than that outside. So, that looks like a process where it somehow violates the natural direction of things, where we're used to seeing a video of the time evolution of some concentration, and we always expect to see the concentration smoothing out and a transition from higher concentrations to lower concentrations. Here, what we're going to see is that there are tons of biological examples that defy that. And in some sense, what I get out of that is, in the same way that, in quantum mechanics, sometimes there are effects that we think of as being counterintuitive, but the way I might characterize it differently is to say that our intuition is flawed and that we need to develop a new intuition. And so, despite the wonders of diffusion, a great subject that we really sung the praises of earlier, in fact, in biology, lots of times diffusion, even though it's our null hypothesis, is not what's going on. What's going on instead is some sort of active process. So there's this really beautiful paper by Daniel Zuckerman. Let me just circle his name so you can make a point of oops, that's kind of weird, going and seeing his work. He's in Oregon, and if you look at his Google Scholar page, or alternatively go to his website, you'll see that he has both a really nice series of vignettes, basically written vignettes online, and then he has a very nice book, Statistical Physics of Biomolecules. And I just think this particular example is a very clever one, which in a way comes down to even the way we think about newness in science. To me, this is really, it's a very nice synthesis of something that often is described almost like by a magic wand, where he shows us that simple principles of physics can help us understand very important biology in a clean way. And to me, in my world, that constitutes a new result. Synthesis matters. In fact, I'll be grandiose and say that never in my understanding of the history of science have we been so in need of synthesis. And I'll probably give a vignette on that. When I say synthesis, that means, bringing together the results of all of the vast literature. When I do talk about synthesis, one of the examples that I'll surely use is from the 1930s, where Hans Bethe, a very noted physicist, tried to bring together under one intellectual roof all the work up to that time on nuclear physics. He wrote 3 long articles in Reviews of Modern Physics that are often known as the Bethe Bible. And in so doing, he basically provided a roadmap for people so that they could understand the entirety of the subject, which was scattered throughout the literature, as is our modern biology and biophysical literature. So anyway, Zuckerman is in my mind somebody doing really, really interesting things, and we're going to imitate him. So what we're going to do here is we are going to examine a concrete case study in which this particular biological battery is used in order to provide a driving force in order to produce a process that is uphill, if you'll let me use those words, although it's actually not uphill, and that's the whole point. It's downhill. It's a free energy downhill thing. It's just that if we focus on the sugar molecules, that contribution to the overall free energy is positive, but there's a corresponding negative contribution due to the flow of hydrogen ions down their gradient. And in fact, if you want, you can think of that as outweighing the cost of the uphill thing. And I'll elaborate on that as we go along. And that was really the point of the Zuckerman article. So here, I just want to show you this article, which is a nice one. You can find it on the archive. The reason I like this one in particular is that it gives both sort of a biological background to the general topic of secondary transporters. And as you can see here, it says, right here, right here. It says secondary transport is driven by an electrochemical gradient in a driving ion, namely sodium or protons. So the point is that we're not, in this case, thinking explicitly about the consumption of ATP. ATP's already been consumed elsewhere in order to produce this gradient, for example. Or alternatively, there's been some sort of combustion of a sugar. But the net effect is that there is this biological battery of the gradient, and the gradient is all we need in order to drive the symporter or the antiporter. Now, this is from the article that I show you above, and it's meant to just point you to a particular example of a structure. And their little schematics shown right here, they show us the two conformations. Now, you'll remember that I gave a little discourse on allostery. And what I want you to note is that there's been a conformational change. So this is the outward pointing configuration. Two ligands come in, the ion and then the thing that's being transported. And then what happens is that this guy undergoes a conformational change, and I'm going to call it an allosteric change. And now they're on the other side where they can be dumped into the inside of the cell or the outside or whatever. It doesn't matter which direction we're thinking about. The main point is that people have worked out the crystal structures of some of these molecules, sometimes in only one of the conformations, sometimes in both of them, etc. And what I want to note is, in a way, that there's sort of this cartoon level understanding. And what we're going to try to do is mathematically build on that cartoon level understanding in order to think about the behavior of such symporters. So here is the picture of what we're going to imagine. So notice on the left what I'm going to refer to as the before configuration. What do I notice about the before? I guess I should highlight that this is in, this is out, and what you can see is that for the pink ions, going into the cell is downhill. On the other hand, for the blue guys to go into the cell, that's uphill. And when I say uphill, I just mean going up their concentration gradient. The whole essence of this story, in a way, and maybe we'll try to work this out when we talk about the MWC model of allostery, is that this symporter right here, this object, this molecule, it's basically demands the binding of both the pink and the red, both the sugar and the ion, in order to undergo its conformational change. So you can think of that as an AND gate. That molecule behaves as an AND gate. It needs A and B in order to be activated. And there's a whole series of stories that that one can write about that. There's a really nice paper by Andrew Mugler and Peter Ryan Tenwolde, a very beautiful paper that they worked out that shows you how allosteric molecules can be used to form the various logic gates, or exclusive or, NAND, AND, etc., just at the level of a single molecule. In other words, you have two input ligands, and so for every state, so that means that that I can have the blue side bound or not, I can have the red side bound or not, and then for each one of those states of occupancy, I can either have the symporter active or inactive. So there's a whole suite of possible logics, and what they do is to work out all of those things. So for the symporter, what we're looking for is AND behavior. The reason I call it AND, again, is because I need both red and blue to be bound, and when they are, this thing undergoes the conformational change and spits the red and blue guys out on the other side, as you see here. What the net result is that the number of blues on the right-hand side has increased, and the number of reds on the right-hand side has increased. For the reds, that means they've gone downhill. For the blues, that means they've gone uphill. You can see over here, in this guy, there's hardly any blue guys, any sugars left on the left-hand outside, and now there's quite a few sugars on the inside. That is because the symporter has basically sent them uphill. I wanted to say, because this is going to be a homework problem, that we could also consider the case of an antiporter. It's still an AND gate, but now, in this case, the pumping is in the opposite direction. In other words, one of the molecules goes in one direction, the other goes in the other direction across the membrane. How one conspires to do that at the level of the protein is an interesting problem in protein design, if you want to think of it that way. For my purposes, I'm very happy to be in statistical mechanician mode to say, consider a molecular object who has the properties of that It undergoes a conformational change when both A and B are bound. The nature of that conformational change leads to a particular direction of fluxes of red and blue molecules. And you can imagine any and all of the different scenarios for which way the molecules go. Again, as I said earlier in my allostery vignette, the particulars to me are at the level of homework. That is not to say that at the level of the kinds of things that the group of David Baker does, which is to design proteins from scratch, that's another universe. I'm in the coarse-grained world where I assume that the protein already exists, and I now try to boil off all the fat and turn it into a statistical mechanical entity with a few kinds of discrete states and with a particular logic. And when I say logic, I'm not talking qualitatively, I'm talking very concretely in the sense of and, or, exclusive or, NAND, etc. Okay. So with all that being said, we're now ready to examine this problem mathematically. Now, I should say that I basically already worked all this out ahead of time because it's a bit arduous for me to write it out in real time. I risk making mistakes and so on. And so what I will do is I will walk you through the math that's sitting here. And of course, one of the beauties of having this in recorded format is that if you want to stop the video and do the arithmetic or the algebra or the calculus or whatever for yourself, of course, I think that that's a great idea. So anyway, okay, here's the situation. So we have an out and we have an in, as already shown in my earlier diagrams, but now I'm in my hand-drawn world. And now I ask you to remember that, implicitly, I have some sort of a notion that dn sugar by dt, and this is in, is going to be equal to minus some driving kinetic coefficient times the rate of change of the free energy with respect to sugar in. In other words, what I want to do is I say that the driving force, and note the units of this thing I'm calling driving force are not force because n is got no units, so the units of dF by dN are energy. Okay, so just be aware of that. It's a sort of a generalization of what we mean by driving force. So the delta, so dF by dN, you'll recall, like if I stop for a moment, note that this thing right here is the discrete version of the derivative. In other words, that is f of n plus 1 minus f of n divided by delta n, but delta n is 1. So that mu is, another way of thinking about mu is df by dn. There's 4 contributions to the total free energy. What are they? Well, I focus first on the outside. On the outside, I have a certain number of reds and I have a certain number of blues. And when I transfer one of the reds from the outside to the inside, what I've done is I've reduced the number of reds on the out. I've reduced the number of blues on the out. And that means that I pick up a factor or a term of the form minus mu. And the reason I say that is, remember, mu is defined as f of n plus 1 minus f of n. And so when I remove a particle, when I go from, when the final is n minus 1, that means that I have minus mu. You see what I mean? In other words, I'm claiming that minus mu is equal to f of n minus f of n plus 1. And that's the situation that I have when I look at the outside. So you can see here that I have a minus mu ion and I have a minus mu sugar on the outside. So the drive is the negative value of the chemical potentials on the outside. Then on the inside, what happened is I increased the number of ions and I increased the number of sugars. So since I increased, that means the final state has one more particle than the initial state. And that means that the thing that I want is plus mu. And so the total change in free energy, the drive with respect to n, which is the number of sugars in, the total change is given by this beautiful and simple quantity. And I just want to say again, this is the incredible power of Gibbs's idea of the chemical potential. Why do I say that? Because I can think of the differences of all the chemical potentials as giving me the degree of disequilibrium. To go back to our earlier treatment of the phenomenological linear transport laws, now we're doing better than that. We're actually saying we can go beyond linearity. What we really want to notice is that the driving force is given by the differences in basically the chemical potentials of all the pieces. Now, I expect you to recall from our earlier discussion of chemical potentials, we worked this out. If you don't remember, go take a look at the vignette on chemical potentials. The chemical potential I defined earlier is free energy of n plus 1 minus free energy of n. For our lattice model of solution, it's strictly entropy, really. And the entropy gave us this log of C over C naught. I can always rewrite that as log of number of molecules divided by the volume. And finally, I can work out all of the entirety of the driving force like this. So let's stare at it. So the first term, the first piece is minus the chemical potential of the ions outside. I have minus signs because I'm going to decrease the number of particles. The final state has one less particle, not one more. What are the entities? I have n ion out divided by V. I'm doing a contrived model in which I'm going to pretend that the volume on the outside and the volume of the cell are equal. You could, of course, amend that, and that's fine. But for now, I'm going to do it in that language. Then the chemical potential of the sugar on the outside is given by this, where I have the numerator in the log as n sugars out. Similarly, I have a contribution for the ions on the inside and the sugar on the inside, and that is the total driving force. So note that it's a bunch of logs, and now what I want to do is I want to acknowledge the constraints. Okay, so here's the way Zuckerman thinks about this problem, which I think is great pedagogically. The detail of how to amend it in the case where you don't assume all these equalities is straightforward, okay? But what we're going to do is we're going to assume that the total number of sugars and the total number of ions is the same. That's one of the things we're going to assume. Fine. Given the truth of that statement, then it's true that n sugar out is given by n tot, the total number of sugars, minus the number on the inside. That's conservation of mass, if you like. Now, what about the number of ions? Well, this is a very cool thing. So the number of ions in is the number of sugars in minus n0. This n0 thing is a way for us to acknowledge that there's a pre-existing gradient in the ions. That's very, very important. In order to get drive, we've got to make sure that there's more ions outside than on the inside. That's going to give us the fuel that's going to allow us to pump the sugars. So I have more sugars on the outside ions on the outside than the inside, and that's represented by this relationship. And then finally, the number of ions on the outside is given by this. So fair enough. So note that this is basically number of sugars on the outside plus n0. As I said before, the number of sugars outside is, number of ions outside is greater than the number of sugars outside. So let's just take a look and make sure it all adds up. So I'm going to take a particular numerical case study. So imagine that the number of ions outside is 100 and the number of ions on the inside initially is 0. So that's our drive. And now what we're going to do is we're going to assume a 50-50 composition of sugar. So the number of sugars on the outside and on the inside is the same, just for ease of interpretation. This implies that n naught is 50, and I'm going to use n tot as 100. So the driving force, if you go back upstairs and you look at all of my chemical potentials, first of all, I want you to notice all these guys cancel each other out. So the additive constants are 0. So all I'm left with is these logs, and if I put it all together and use the rules of logs, log of A plus log of B is log AB, and log of A minus log of B is log A over B, then this is the statement of the driving force. Now, and by the way, let's check that equilibrium corresponds to 0 driving force. What is the equilibrium going to be? The equilibrium is going to be the number of sugars in is going to be 75 out of 100. The number of ions in is going to be 25 out of 100, and the number of sugars out is 25 out of 100, and the number of ions out is 75. In that case, this full product ratio of products is equal to 1 and the log of 1 is 0. So there's no driving force. So that's useful. Using the constraints on the various numbers, I can write everything in terms of one variable, which is the number of sugars in. This is a constrained problem. There's only one parameter, which is the number of sugars in. And that determines the driving force. And what I want to find out is, as I shift n sugar in, what happens to the driving force? Because at the minimum in free energy, the number of sugars in will be some value. And when I find that value, then this whole quantity will be 1, and the driving force will vanish. So I can rewrite all this by dividing top and bottom by n tot, which is what I've done here. If you look carefully at the two expressions, you'll see that this expression, this one, and this one are the same. All I've done is divide top and bottom by n tot. And that leads to a very nice simplification where I've defined x is equal to n sugar in divided by n tot. I've defined n0 over n tot as f, and in that case the driving force is of this form. Very cool. So now, the change in free energy is less than 0. The change in the number of sugars, therefore, has got to be greater than 0, because the net of these two quantities together, it's basically the second law, has got to be less than or equal to 0. Another way to say it is that when we're moving in and out of the equilibrium state and we're moving towards the minimum, we're bringing the free energy down. We've got to make sure that if the change in free energy is negative, then that means the change in the number of sugars in has got to be positive. Okay, so just as a reminder, this thing is df by dn, basically, and then this is dn sugar in, and this thing has got to be less than or equal to 0. So if this piece is less than 0, that implies that this piece is greater than 0. That's the usual sort of second law argument. So we're basically almost done. So now let's look at the driving force. So what you see is that the driving force, if we start over here, remember we started out at 50-50. So here's the starting point, 50-50. And in that case, the dn by dt is positive. Why? Because what we're measuring, let me write that. dn sugar in by dt is minus gamma, and then df by dn sugar in. I told you this is a one parameter story. If this thing right here is positive, that means dn sugar by dt is positive, which means that the number of sugars in is increasing. So that's this side of the curve. We're going to come down this curve, that's the drive, until we reach the fixed point, which is right here at 0.75. If we had started with too many sugars in, actually, then the free energy minimization would have taken us back in this direction. So what we see is that this out of equilibrium dynamics keeps pumping us towards this fixed point, which effectively leads to a pumping up the gradient of sugars. So that's the point I wanted to make. Now, we can write down the differential equations. I already showed you what it was. Note that we know that dn sugar out by dt is going to be minus dn sugar in by dt. That's because of the stoichiometric coupling and also the conservation of mass. And we know that dn ion out by dt is going to be equal to, so dn ion out is going to be negative, right? So that also is going to be equal to minus dn sugar out by dt. And finally, I can write the last one, which is dn ion in, and that's going to be equal to dn sugar in by dt. Wait, sorry, I think I screwed up this last one. let me just think about this. So, yeah, Dn ion in. Yeah, this. Sorry, I said this wrong. Dn ion out by dt is negative. So that means it's got an opposite sign to dn sugar in by dt, which is positive. So, okay. Note also, that this thing reaches a steady state. So what we're seeing here is let's remember our initial conditions. We started out with half and half blue, so half sugar in and half sugar out, and we started out with all the ions out. So that's this, all the red ones there, and this is the 50-50 partitioning of sugars. So that's our initial condition, and what we find is that over time, the number of sugars in goes up, the number of sugars out goes down, the number of ions out goes down, and the number of ions in goes up, and they reach a steady state. It'll actually stop. It'll stop pumping at some point, right? Now, here's the last point that I guess I want to make in this vignette, which is this thing's going to keep on working ad infinitum, and we need to think about one last point. In fact, the cell is going to pump the ions back out again in order to keep the drive, in order to keep the biological battery of the pink ions charged. How does it do that, and how is it worth it? I want to remind you of this. So in particular, I want to remind you of this amazing fact. How much energy is stored in sugar? So look at this monstrous number, 1200 kT. So the point of this is, if I am able to bring a sugar on board, that's worth 1200 kT. I can convert that into some 30-something ATPs, and I'm perfectly happy to expend a couple of those ATPs to pump the hydrogen ions back out again. There's no sense in which I'm violating any energy conservation, because there's tons of energy left over due to the fact that I brought that sugar on board. So, back to this picture, I'm giving you a qualitative story, but what I'm saying is that here, when we reach this state, these ions are going to be pumped back across at a certain cost, and that cost is basically the proton motive force, the cost of the proton motive force, which is of order 1530 kT, in comparison with the giant 1200 kT. So what I hope you got out of this is a good sense of how the biological battery of the membrane, basically the membrane gradient of hydrogen ions, can be used to do something really, really interesting, which is to pump sugar molecules upstream, and then how those sugar molecules can be metabolized, turned into ATP, which can be used to continuously create the hydrogen ion gradient, and thus keep that particular battery charged. Okay, so with that, we're going to next think about the ATP battery, but I hope you enjoyed this case study.